everyone, I'm Shuangshuang Jin from CASP London. My individual project is dynamic dispatch, prioritization and allocation of ambulances to patients. The following presentation includes 4 parts. I will introduce my project first. Dynamic dispatch is the mechanism that assists in deciding what operations should be executed to realize optimal deployment of existing resources. This project implements several algorithms to realize the forecast of available medical assistance resources and ambulance demand, build a data-driven method to optimally allocate resources to patients in need. The motivation for choosing this project is its practicality. The London Ambulance Service handles almost 1.6 million calls across London and sends a physical response to more than 1 million incidents each year. Emergency medical service lays the foundation for the personal safety of residents in daily life. A 1-minute reduction in ambulance response time may save more lives. The demand for optimizing the existing ambulance dispatch system is imminent. And for the most complicated parts in my project, the first one is to utilize proper models to predict different medical assistance duration, ambulance travel time, and incidence occurrence. The second one is how to design an effective medical vehicle dynamic dispatch algorithm and evaluate, which needs theoretical support and technical exploration. In terms of my aims and objectives, the first one is implementing methods of neural models, neural network, and time series analysis to realize forecast. After training and testing models, I can get optimal parameters. Another one is to create the ambulance dispatch system based on the predicted data, selecting the most time-saving ambulance to implement fast response medical assistance. The recommender is intended to shorten the patient's waiting time. The data source of the project is London Ambulance Service and London Data Store. I collected daily rainfall data from London Data Store. It is used as a supplement variable when forecasting data. And the following 3 datasets is provided by London Ambulance Service. Incident data includes date time, location, incident priority, C1, C2, C3, and C4. For example, C1 is of the highest priority, which means immediately life-threatening incidents. Responder group: Fast Response Units (FRU) and Double-Crewed Ambulances (DCA), and call sign, the tag for each vehicle. It is used to predict future incident occurrence. While vehicle movements dataset contains date time, incident ID, call sign, ambulance status, and location. All responder group of this dataset is FRU. It is for travel time prediction part. Emergency medical service intervention data involves date time and the corresponding responder group. The predictive duration of medical teams' interventions can be derived from it. I applied autoregressive model to predict medical teams' intervention duration. The mean squared error of the results only account for a small percentage of the true value. To sum up, the overall effect of the forecast is precise. As for the ambulance travel time prediction, I utilized fully connected neural network model. This approach takes date time as only a variable value. By observing the result, the divergence between the text and the trained data is relatively small. Autoregressive Integrated Moving Average Model (ARIMA) is based on time series analysis. That is, the date time is the index of the dataset. I tried this method to predict ambulance travel time and incidence occurrence. This approach is based on time series analysis. That is, the date time is also the index of the train and text dataset. Based on the date time and location, the travel time can be roughly predicted. Then I used long short-term memory model (LSTM) to predict ambulance travel time and incident occurrence. This approach is based on time series. ARIMA model does not perform feature extraction on the input data, while LSTM model adopts three-dimensional input vectors, which include the number of samples, the data dimensions, and time step. Compare the different models above by loss inclusion. For the prediction of incident amount, the ARIMA model performs better than others in short-term forecast, while the multiple feature LSTM model is more preferred for long-term forecast. There are two contributions in my project: ambulance dynamic dispatch system and ambulance pre-allocation recommendations. The second one is based on the previous prediction of incident occurrence. I will explain the ambulance dynamic dispatch algorithm in detail next. By analyzing data, the incident density is two-spreads in original data. According to the heat map here, even in the most frequent part, the dark red one, there is less than 3 incidents of one type happened in a day. So, a dense dummy data set is generated based on the characteristic of the original one. Suppose that an incident happens in brick E. The system will dispatch ambulance from E and its 8 adjacent bricks. The patient's waiting time equals to ambulance intervention duration plus travel time. The algorithm aims to minimize the waiting time. The first allocation method is to assign a currently available ambulance. The second allocation method is to dispatch a currently unavailable ambulance to it. By traversing all ambulances in these 9 bricks, if the ambulance is available, the waiting time is the predicted travel time between the start brick and the end brick. If the ambulance is unavailable right now, the waiting time is the remaining ambulance intervention duration past the predicted travel time between the 2 bricks. Here is an example of the recommend system. Here is the result. The second allocation method saves 7 minutes than the first one. In conclusion, history average data provides valid reference when estimating current or future cases. This project realizes the prediction of available medical resources, ambulance travel time among different bricks, and build a dynamic dispatch system which saves patients' waiting time to a certain degree. There are still several limitations in my project. First, the ambulance dynamic dispatch algorithm is tested with dummy data and it is not sufficient enough. And the span of the original data is only 1 year. The characteristics of the time series in result are not significant, so the accuracy of pre-allocate recommendations needs to be improved.